Module 12C, we're going to start examining some other properties that are related to intermolecular forces, specifically the vapor pressure and boiling points of substances. You should also be able to apply and define concepts of vapor pressure and boiling point, and know definition of boiling point, specifically normal boiling point and normal melting point. What does this word normal mean, and why do we specify it? So first, let's talk about what is vapor pressure. What do we mean by the term vapor? Well, what's the difference between a vapor and a gas? This concept of vapor is used to describe a substance that's in the gas phase if gas is not its most stable form at that temperature and pressure. So what I mean by that is like looking at water. Let's look at H2O at 1 atmosphere at 25 degrees C versus 200 degrees C. Water at 25 degrees C, or H2O, to make it simpler, if you don't want to think about it, because water kind of refers to a phase. Let's think of H2O at 1 atmosphere, 25 degrees C. Can it be in the gas phase? Yeah, it can. Water doesn't actually boil until 100 degrees C, but there's water in the air around us. There's water vapor in the air around us that we're breathing in, that's being condensed. If we get a cold drink of water from the fridge, we put ice in our water, the outside of our glass will get condensation on it, and that's from water from the atmosphere. If I leave a glass of water out on the tabletop, over time that water will evaporate away. The water evaporates away as a vapor. So how is that happening? Well, that's vapor pressure. At 200 degrees C, I absolutely expect the water to leave the liquid phase and escape to the vapor phase. But at 25 degrees C, I don't. So at 25 degrees C, that's actually a vapor, not a gas. It is in the gas phase, yes, but usually H2O gas refers to something like actual gas molecules that we expect it to be. Instead, we refer to it as a vapor because it came from a system that should not be in the gas phase at that pressure and at that temperature, but it is. So to try to better describe this, I want to talk about this thought experiment here. Let's pretend we have this box. It's an evacuated meaning completely emptied, under vacuum, completely evacuated chamber. It's 0 torr. And I place 1 ice cube inside. So we've got our single ice cube inside of here. I then slowly heat up this system, heat up this evacuated chamber, and I allow the system to reach room temperature. This is over time. So slow warming up, I reach room temperature over time. I'm now at 25 degrees C. 25 degrees C is just the relatively universally accepted point for room temperature. Most room temperatures anywhere between 21 and 26, but 25 is kind of our standard room temperature. So over time, I let this system this evacuated chamber slowly warm up and reach 25 degrees C. What do I expect to have happen? Well, I expect that the ice melted, right? I expect to find liquid water in here, hence the liquid water here. This is all my liquid water. But if I analyze the components of the system, I would also find H2O in the gas phase in that chamber. Even though I have not reached 100 degrees C, I would find water vapor present. That is because water has a vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid state. So the water has escaped, some of those water molecules have escaped the liquid phase and entered into the vapor phase. These are now in what we call an equilibrium. And you will cover equilibrium in a different chapter, but basically what's happening is these water molecules are condensing back down to form liquid as some of these liquid water molecules are evaporating out to form your gas. And this is happening at the same rate. So I've got H2O gas condensing back down to form H2O liquid. And at the exact same rate, I've got H2O liquid evaporating to form H2O gas. The vapor pressure is the pressure that's exerted by these gas molecules. It's the pressure exerted by a vapor in equilibrium with its liquid or solid state. It is called a dynamic equilibrium. So basically the gas to the liquid, the gas condenses down to liquid at the same rate as the liquid evaporates to the gas phase. It's at the same rate, which means overall concentration, the concentration of water in the liquid phase to the concentration of water in the gas phase remains constant because it's in a closed system. If it was an open system, such as out of my tabletop, the water would eventually all evaporate away. And of course, we're going to see that, temperature can affect this, pressure affects this, etc. So, the stronger your intermolecular forces, the lower your vapor pressure. Basically, the stronger your intermolecular forces, the stronger it is holding those things together. Vapor pressure exists because these particles are able to escape their liquid or solid phase into the gas phase. If I've got stronger IMFs, stronger forces holding these together, it takes more energy for them to escape solution and go into the gas phase. So the stronger the intermolecular forces, the lower that vapor pressure will be, because there'll be less particles in your vapor phase. For a given liquid, the vapor pressure will increase with temperature. Basically, as I heat it up, I'm giving those particles more energy, which allows them to more easily escape their liquid phase, even though they haven't reached temperature to truly boil, like we think about a boiling point yet. Example of that is growing up, my mom's home was built in 1924, so we don't have a central heating system. We have radiators and a furnace in our basement. And so to keep the air from being too dry, we would put ceramic bowls of water on the radiators in each one of our bedrooms throughout the winter. And we'd have to fill those bowls up every couple weeks with water because all the water would evaporate away. The water wasn't boiling. It was never reaching 100 degrees C, but it was evaporating away at a faster rate because it was warming up the water because it was sitting on top of a radiator. So as I increase that temperature, the vapor pressure will increase. It's all about how easy is it for this molecule to escape being attached to another molecule in solution. How much can I break this apart? The higher the temperature, the easier it is to break that apart. A liquid is considered volatile if it has a vapor pressure, meaning it's easily vaporized. If something is able to enter the vapor phase, it is volatile. That means it doesn't actually boil, but the volume that you visibly see will be decreasing. Things that enter into the gas phase easily. So things like if you spray a perfume, you spray an air freshener, those are liquid in their can or in their container, but they come out as a gas. And then they spread those, oftentimes like perfume, used to make, because it smells good, it spreads that as a gas phase. The stronger your intermolecular forces, the less volatile a substance. So the stronger those intermolecular forces, the closer they hold them together, the more difficult it is for it to escape the solution it's in, and therefore the less volatile it is, because it's not gonna easily enter into the vapor phase. So for example, diethyl ether versus ethylene glycol. Diethyl ether looks like this. And looking at this molecule, everything has LDFs. But this also has dipole-dipole. It's weak though. Technically this oxygen is more polar, but it's a weak polarity here. Diethyl ether has a boiling point of 35 degrees C. It is very volatile. You can actually hold this in your hand and boil it with your hand because body temperature is 37. So it easily escapes into the vapor phase. It has a high vapor pressure. It's very volatile. Ethylene glycol, on the other hand, looks like this. This also has LDFs because everything does. It's polar, so it has dipole-dipole. But it also has hydrogen bonding. This is not very volatile. This boiling point is 197 degrees C. It has a very low vapor pressure and a low volatility. Diethyl ether easily escapes into the vapor phase. Ethylene glycol does not. And it's because of those intermolecular forces. Diethyl ether does have dipole-dipole, but they're very weak dipole-dipole, just because of the overall geometry of the structure. Whereas ethylene glycol has the hydrogen bonding going on. So I know this isn't the best picture, and I apologize. This is how I recreated it. But what I want to look at here is we've got your temperature versus your vapor pressure, and these are the actual boiling points of the system. So what we see here is your vapor pressure increases as we increase temperature. The stronger your IMFs, the lower your vapor pressure, and the less volatile that substance is. Looking at diethyl ether versus ethanol versus water versus ethylene glycol. Diethyl ether, we just looked at, but it's got that structure. CH3, CH2, O, CH3, CH2. Or CH2, CH3, I apologize. If you want to see it drawn out, go back to just a little bit the previous slide, we did that. Ethanol has a CH3, CH2OH. Water, of course, we know. And ethylene glycol, we also just drew out. Diethyl ether, we see we have LDFs and weak dipole-dipole. All of these three, the ethanol, the water, and the ethylene glycol, we have LDFs, dipole-dipole, and hydrogen bonding. They're all leading to a higher and higher boiling point. So again, this is what listed. These values down here are their actual boiling points. So diethyl ether boils at 35 degrees C, ethanol 79, water 100, and ethylene glycol 197. If they all have LDF, dipole-dipole, and hydrogen bonding, though, why do we see this difference in boiling point? I thought we said that it would go by molar mass. Kind of. It also goes by geometry of the structure itself. Ethanol, though it does undergo dipole-dipole and hydrogen bonding, ethanol has this nonpolar component to it. This CH3-CH2 group is nonpolar, and it does take up a lot of space. If you draw out the VSEPR structure of this, you're going to see the space it takes. That space that it takes up, the physical space it takes up, takes away from the hydrogen bonding that the compound's going to undergo. That's why water has a higher boiling point than ethanol. It's not a huge difference, 21-degree difference, but that this grouping here does create a space issue where they can't quite meet together as tightly as they want to by themselves. Ethylene glycol, we've got hydrogen bonding occurring on both sides of the molecule, and we see almost a doubling of that boiling point here. Another thing to note on this graph, a substance exists as a liquid at the temperature to the left of the line and exists as a gas at the temperature to the right of the line. So we're going to talk about boiling point in just a sec, but this line here is marked for a reason. This 760 torr. Note that where this line crosses is where I hit my boiling points. So in diethyl ether, we see this curve up. When it crosses that 760 is when I reach the temperature of my boiling point. Water crosses, reach my boiling point. And same for, or ethanol, same for water, same for ethylene glycol. Boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure, and these are defined on the next slide, so I'll slow down there. But the normal boiling point is the temperature at which the vapor pressure of a liquid equals 760 torr. So the values you see when you look up the boiling point of a compound are reported at 760 torr. It's the vapor pressure of the substance at 760 torr specifically. That's what your normal boiling point is. So, some definitions here. Boiling point itself, the temperature at which the vapor pressure of a liquid equals the external pressure. So, boiling points can change. It does depend on the external pressure you're at. And that's why things like pressure cookers work. We talk about Mile High City, stuff like that. Boiling point in general is the temperature where the vapor pressure of a liquid is equal to your external pressure, regardless what your external pressure is. Normal boiling point is used because it's the temperature at which the vapor pressure of a liquid equals 760 torr. This is so that we can compare to other scientists. We can compare to other people. We can say water boils at 100 degrees C. Does water always boil at 100 degrees C? Truthfully, it depends on the external pressure. Depends where you reside, where you're at that moment. But if I'm at exactly 760 torr, water will boil at exactly 100 degrees C. The stronger your intermolecular attractive forces, the higher your boiling point becomes, because we have to overcome those IMFs. We have to break apart those IMFs. We need energy to do that. The melting point or freezing point is the same point. So something melts at the same temperature it freezes. That kind of throws students off. So I want you to think about that. Water will melt at 0 degrees C. Water will freeze at 0 degrees C. So your melting point, freezing point is the temperature at which a solid and liquid states are in equilibrium. I can go either direction there. So if I've got something at exactly 0 degrees C, I'm in an equilibrium. I've got my liquid and solid phases completely in equilibrium at that point. If I drop the temperature down just a little bit, I'm going to freeze my sample. If I raise the temperature slightly, I'm going to melt my sample. If I stay at exactly 0 degrees C, I'm in a true equilibrium between my liquid and solid phase. The stronger the intermolecular forces, the higher the melting point. Same reason as for boiling point, it takes more energy to break them apart. The lower your external pressure, the lower the boiling point. If the external pressure is less than 760, say it's 745, it's easier to reach the vapor pressure of your substance, hence your boiling point has been lowered. The higher the external pressure, the higher the boiling point. Let's say the external pressure is actually 780, now it's going to take more work to reach a vapor pressure of 780, so our boiling point is now higher. So some examples of boiling points of water at several locations with varying altitudes. We see Mount Everest, Tibet, the highest mountain peak on the earth. Our elevation is 29,000 feet, and the approximate atmospheric pressure there is 0.32. Remember, 1 atmosphere at 760 torr. So water boils here at 78 degrees C. Pretty low, right? Boston, Massachusetts is approximately Boston, Massachusetts at sea level, approximate pressure of 1 atmosphere, so 760 torr, and we get water boiling at 100 degrees C as we expect. Denver, Colorado is Mile High City, elevation of 52,000 feet. Approximate pressure is 0.83 atmosphere, and water will actually boil at 94 degrees C. So again, this is why things like you see different temperatures for different altitudes of where you're at. It's how pressure cookers work. Pressure cookers work by bringing that pressure, cooks the food faster. The stronger your IMFs, the higher the boiling point, the higher the melting point, and the more likely the substance is in a condensed state of matter at room temperature. What do I mean by condensed? Condensed is a liquid instead of gas. Or you can even say solid is most condensed. So for boiling, I want you to think about boiling occurs throughout the body of the liquid. When boiling water, the bubbles of steam, not air, form when the vapor pressure in the bubbles is equal to the atmospheric pressure. They also rise, so it's less dense. So how can water boil at a temperature less than 100 degrees C? But how can water boil at a temperature greater than 100 degrees C? This is all based on your vapor pressure. Once liquid is boiling, adding heat only makes it boil more quickly. It doesn't actually raise the boiling temperature. It's going to boil at that temperature. It reaches an equilibrium. And students kind of get thrown off as like, but no, more heat will make it boil. You know, it's still boiling at the same temperature though. If you continue on to organic chemistry, when you take organic, you're going to do experiments where you're going to distill things, which means you're going to boil things, and you're going to monitor the temperature at where they distill. And you're going to see that your sample holds steady at that boiling point because you have reached an equilibrium at that point. Which substance is a liquid at room temperature? The other one would be a gas. To look at these, you would have to think about their structures. If I have CH3OH, that's methanol. It's an alcohol. It's known as wood alcohol, and it's what people drank during Prohibition. Everything has LDFs. This is polar, so it has dipole-dipole. And it follows the rules for hydrogen bonding. What about CH3CHF2? Remember the way that this is drawn tells me how it's connected. CH3 after the C tells me that the hydrogens go on this carbon. But I know carbon wants 4 bonds. Next thing listed is a carbon. Hydrogen here. Hydrogens can only have 1 bond though. So these fluorines, who can also only have 1 bond, must be attached to the carbon. This also has LDFs. It is dipole-dipole because it is a polar molecule. But I do not have any hydrogens attached to my fluorine, so no hydrogen bonding, which means this is going to be my liquid at room temperature. What about CH3OCH2CH3 or CH3CH2CH2NH2? I'm going to let you guys draw these out, but what you should find is this has LDFs and weak dipole-dipole. When you draw this one, I want you to remember the pattern. Those hydrogens go to that carbon. Carbon wants 3 bonds. Those hydrogens to carbon, those hydrogens to carbon, these hydrogens to the nitrogen. Carbon always wants 4 bonds. Nitrogen prefers 3 with a lone pair. You should find that happening here. This is LDFs, dipole-dipole. And if you draw this out correctly, you will have nitrogen bonded to carbon with other things here. And you can see that this can clearly go hydrogen bond. So this will also be a liquid at room temperature. The boiling points for 3 molecules are listed below. Predict the choice that matches each compound with its boiling point. Remember, boiling point is higher when your intermolecular forces are stronger. So -33, -89, and -188. I've got F2, LDFs, and that's it. Got C2H6. Remember, hydrogen can only have 1 bond, so this is the only way I can connect this is like this. This also only has LDFs. And I've got ammonia. This has LDFs. It is polar. And it will hydrogen bond. So now we just need to figure out F2 versus C2H6, which one's going to have the higher mass here, or higher boiling point. When I look at mass, it's not exactly the most helpful thing because carbon has a mass of about 12 AMU, hydrogen about 1, So C2H6 is about 30 for the mass unit. F2, fluorine is, I believe, I'm doing this from memory, so I could be wrong, but I believe it's around a mass of 19 for one fluorine atom, so about 38 for F2, which would suggest that fluorine would have a higher boiling point because they only have LDFs. But that's not actually correct in this case. It's not so much about the boiling point, it's about the size of the molecule as well. C2H6 is just a bigger molecule than F2 is. Fluorine is the smallest atom we have, and so smallest atom we have, it's bonded to itself versus C2H6, which is just a bigger molecule. The bigger molecule means it's more polarizable, which means that it's going to have a higher boiling point. So this is going to be F2. This will be C2H6. And our final answer is D. Okay, another thing we want to talk about really quick is kinetic energy curves. So temperature is a measure of your average kinetic energy. We talked about average kinetic energy, E sub K, when we discussed gas laws. Remember, your average kinetic energy is just based on your temperature. At any temperature, there's always some particles at the surface that have enough energy to escape your attractive forces of the liquid and become a gas. Always. The larger your surface area, the faster the rate of evaporation. Because if you've got more particles here at the surface, they're more likely to be able to escape. They're not holding in as tightly. The larger, if I have, a diameter like this versus a diameter like this, if I have the same amount of liquid in both of these, this is going to go empty first. As your temperature increases, the fraction of molecules with sufficient energy to escape also increases. So what we're looking at here on this graph, you've got your kinetic energy versus fraction of molecules. This dotted line here is the minimum kinetic energy that's actually needed to escape the system. We see at lower temperature versus higher temperature, more of our molecules are able to escape the solution because they have more energy to be able to do so. With that in mind, can you answer this question? In each figure, the dashed line represents the threshold kinetic energy required to vaporize the liquid. Both substances are at the same temperature. We're not looking at difference in temperature here, so which has the strongest intermolecular forces? I want you to think about this, but then remember what this line means. This line is where the liquid is vaporized. It's the minimum kinetic energy needed to escape. If I look at the portion of molecules under here, portion of molecules under here versus portion of molecules under here, substance B has a lot more molecules that are escaping. So which one has the strongest intermolecular forces? The one who is not as easily escaping. Substance A in this case would have the strongest intermolecular forces because more of them are still holding into the solution.